To understand the breakthrough of SAM3, we first need to look at where we came from. On the left, we have the paradigm used by SAM2, known as Promptable Visual Segmentation, or PVS. In PVS, we provide a geometric cue, like a point or a box. The model responds by segmenting that specific object. It's a one-to-one relationship, one prompt, one mask. This is powerful, but it has a limitation. What if we want to find every instance of an object in a scene without clicking on them individually? Enter SAM3 and Promptable Concept Segmentation. Here, instead of a spatial click, we provide a semantic concept, like the noun phrase yellow school bus. Notice the difference. The model doesn't just look at one spot. It scans the entire image and segments all matching instances simultaneously. This shift from segmenting a visual target to segmenting a semantic concept is the core problem SAM3 solves. Building on the foundation of previous models, let's look at how SAM3 actually perceives the world. It introduces a paradigm called Promptable Concept Segmentation, or PCS. At the core, we have the SAM3 architecture, designed to accept multimodal inputs. Unlike predecessors that relied heavily on clicks or boxes, SAM3 thinks in concepts. First, it accepts text prompts. These are short noun phrases like striped cat. The model doesn't just look for a pixel location, it understands the semantic meaning of the object. Second, it accepts image exemplars. Sometimes, words aren't precise enough. You can provide a visual crop a square showing exactly what you're looking for, and SAM3 will find all similar instances. Crucially, it supports hybrid prompts. You can combine a visual example with a text description. This allows you to refine the search, for instance, providing an image of a car, but specifying red in text to filter the results. Once prompted, the model processes this information to generate the output. But notice here, it returns not just segmentation masks, but also unique tracking ID. This ID generation is key. It means SAM3 can track specific objects across video frames, maintaining their identity over time. Having understood the concept-based approach, let's look under the hood at how SAM3 actually processes this information. At the foundation of the model lies a powerful shared vision encoder built on the Hiera architecture. This component does the heavy lifting, processing raw pixels into rich semantic features. Instead of training separate models for images and video, which would be computationally expensive, SAM3 utilizes a unified design. From this single backbone, the architecture splits into two specialized heads. On one side, we have the image-level detector, optimized for finding objects in static frames. On the other, the video tracker, designed to follow those objects through time. Because they share the encoder, the system is incredibly efficient. But video presents a unique challenge. Objects move and change. To handle this, the video tracker is coupled with a memory bank. This allows the model to store information about an object's past appearance and location, ensuring consistent identification across frames. This unified flow means that whether you are segmenting a single photo or a complex video sequence, the core visual understanding comes from the same robust source. Building on the detector architecture we just saw, let's zoom in on a critical innovation in SAM3, the decoupling of tasks. Standard detectors often try to do everything at once, but SAM3 splits the job into two parallel paths. Top, we have the localization head. Its only job is to answer, if there were an object here, where would it be? Bottom, we have the new presence head. It asks a simpler but vital question: is the concept actually here? Let's see this in action. Suppose the input contains a clear concept. The localization head proposes a bounding box. Simultaneously, the presence head calculates a high confidence score. Because the presence score is high, the gate opens. The system trusts the localization and outputs the detection. Now, consider a tricky case, perhaps background noise that looks slightly like an object. The localization head, designed to find boundaries, still suggests a box. It's hallucinating a location. However, the presence head sees through the noise. It assigns a low existence score. When the box reaches the gate, it is rejected. By validating existence before committing to location, SAM3 significantly reduces false positives. To teach SAM3 to recognize concepts with this level of precision, we use a massive data engine. But how does it actually learn? Let's take a target concept, for example, a wolf. It's easy for a model to match this against a clear positive example, like this image of a wolf. The real challenge lies in distinguishing the wolf from hard negatives. These are images that look visually similar like this husky, but represent a completely different concept. To solve this, the model uses a contrastive training signal. It learns to minimize the distance to the positive match, effectively pulling the concept closer, while simultaneously maximizing the distance to the hard negative, pushing the confusion away. This ensures the model focuses on the subtle semantic differences, not just general shapes. For SAM3, we scaled this process up immensely. The SA-code dataset repeats this for over 4 million unique concepts, creating a robust foundation for open-world understanding. With this massive knowledge base established, let's see how the model architecture actually processes this information.